Okay, we're going to be working on the t-distribution. And one of the requirements for using the normal distribution, which is we've been using up until this point, is that we know the standard deviation of the population. So we have to know the standard deviation of the population to use the normal. And that was signified by that symbol. But we rarely know that. So what do? Well, that's where the t-distribution comes in. And the t-distribution is very, very similar to the normal. When we were working with the normal, we were working with a formula that looked like this: x bar minus mu, the standard deviation of the population, divided by the square root of n. So that was with the normal. Well, the t-distribution is a very, very similar distribution. And it's also mound-shaped. It's centered at 0. But one thing that's different about the t-distribution is there's a different t-distribution or different set of probabilities associated with the t-distribution for every single sample size. Now, we like to make it fancy and say every degree of freedom. Well, degree of freedom just happens to be the sample size minus 1. So there's a different probability set for every t-distribution or every t distribution with a different sample size or different degree of freedom. And that's different than the normal, which had the empirical rule. And remember, the empirical rule had the same probabilities regardless of the sample size. It was tied to the actual mean and to the standard deviation. The t-distribution, there's a different one for every single degree of freedom or every single sample size. The t-distribution is a little bit different than the normal, although they look very similar. So if the dashed line represents the normal, the t-distribution is a little bit shorter, not a whole lot, but a little bit shorter. And the t-distribution has more variance. So the t-distribution has a larger variance and has more area in the tails. It also has less data near the mean. So the t-distributions are going to be a little bit shorter and a little more spread out. In other words, it's going to be a little bit fatter than the normal. All right. Now, we said the z distribution required that you use the standard deviation of the population. Well, the t-distribution formula looks very similar and operates much the same way when we get to the calculator part. But instead, if you look at it, the numerator is exactly the same. But in the denominator, there's one notable difference. Here we have the standard deviation of the population. So this represents the population. And this represents the standard deviation of the sample. So when do we use the t-distribution? We use the t-distribution every time we don't have this. So if I have to use the standard deviation of the sample, I'm going to use a t. If I have the standard deviation of the population, I use a z. It's pretty much that simple. Okay. And so here's a listing again of that formula. All right. So the properties of the t-distribution. There's a different one from every degree of freedom. In other words, for every sample size. For every sample size, there's a different one. We already said it's centered at 0 and symmetric. The area under the curve, because it's a probability function, is 1, and that's true for any of these distributions. Here's something that's very interesting, though. As the sample size increases, the t-distribution gets closer and closer to the normal. So as we increase our sample size, it becomes less spread out and starts to approach the normal. And it's already very similar to the normal, but not the same. This is very key. The t-distribution has more area in the tails than does the normal, and the t-distribution has a greater variance than does the normal. So when can we use it? We can use it when the data is nearly normal and there are no clear skewness or outliers. But the main thing is we're going to look to use it when we have the S, or the standard deviation of the population. So if you have standard deviation of the population, that's when we're going to use this. All right, so let's make some comparisons, and you'll see very quickly on the next page how similar these formulas are up until the calculator part. So a college's data about incoming freshmen indicate the mean of their high school GPA was 3.4. The students are randomly assigned to a freshman writing seminars in groups of 25. So we have an sample of size 25. What is the probability that the mean GPA of the group is less than 3.3, given that the standard deviation of the population is known is 0.35? So they're telling us we know the standard deviation of the population, which is this simple. So this lets me know that I'm not going to be working with a T, I'm going to be working with a Z. And they say that the mean of the population is 3.4. And we want to know the likelihood that we'd have a sample or an X bar less than 3.3. So I'm going to go ahead and make a list of what we have here. So we have mean of 3.4. We have a standard deviation of the population of 3.3. And we have an X bar, excuse me, not 3.3, X mean population of 0.35. We have an X bar equal to 3.3. And we have a sample of size 25. And we want to know the likelihood that we're going to get a value that's less than, or a sample mean that's less than 3.3. That's what I'm interested in knowing. Likelihood of getting a sample less than 3.3. And if I were drawing a picture of this, it would look something like this. We have a mean right here, and that mean is at 3.4. And then we have an X bar right here. We want to know the likelihood that we have less than 3.3. So we can do this with the norm CDF, but first off, let's go ahead and set up our probability statement. So the probability that Z, and our Z formula was Z equals X bar minus mu sigma divided by the square root of N. That's our formula. The probability that Z is less than, well, X bar was 3.3 minus 3.4 over 0.35 divided by the square root of N. So let's figure out the Z-score. We're going to go about doing this the more challenging way, all right? And when we do this, we have to be very careful about how we place this in a calculator. So what's going to be my Z? I'm going to try to find out my Z. And oops, and this should not be an N. We know this value to be 25. So we're going to go parenthesis 3.3 minus 3.4 and close the parenthesis, divided by parenthesis 0.35 divided by the square root of 25, or 25 caret, oops, 25 caret 0.5. And then we're going to close those parentheses. And I end up getting a Z-score. So the probability that Z is less than negative 1.4285. Now I know there's an easier way to do this, but for the time being, I want you to see, I'm doing this to show you the similarities between the t-test and the z-test. I mean, so here we go with the continuing on with the z-test. We're going to go second vars, normal CDF. So I'm going to do a normal CDF. I'll do this here in black. Norm, CDF, lower bound, negative infinity. Upper bound is going to be our negative 1.4285. And because it's a z-score, our mean is 0, and our standard deviation is 1. So let's do this. Second vars, normal, CDF, negative infinity. Upper bound, negative 1.4285. Mean of 0, standard deviation 1. And we end up getting a probability equal to 0.0765. All right, so we get a probability of equal to 0.0765. Now, is there a quicker way? Yes, there is, and I'll show you that real quickly here. We could have gone stats, test, z-test, and I could have put in a mean of 3.4. This is the standard deviation of 0.35, the x-bar of 3.3, sample a size 25, and I end up getting negative 1.4285. All right. So there's obviously a quicker way, but I wanted to show you that what I needed you to see here is that this formula yielded this value, because we're going to come back and refer to this in just a moment. All right. So the next thing is we're going to do a t-star. Now I have a typo here. Let's scratch out this 3 and make this a 3.3 because we want it to match our value up here. We want these two values to be the same. All right, and once again, in this case, we have exactly the same mean. We have exactly the same standard deviation. So, but we need to change our labeling up. So here's what we're going to have as far as our labels. Our mean is 3.4. What's the probability the mean GPA of the group is less than 0.33, given that the standard deviation of the sample, because it's of a sample, this is S. So now I'm going to have to change this. My mean is 3.4. My S my X bar is still 3.3, but my S is 0.35, and my sample is 25. Now, because this required an S, or because this has an S, we're going to use the formula T equals X bar minus mu S divided by the square root of N. All right. Now, if I were drawing a picture of this, wish I had a blue pen available. Maybe I do. Right. So if I were drawing a picture of this, my mean is still at 3.4. My X bar is at 3.3. So my picture is exactly the same. And we're looking for, once again, the probability that X bar is less than 3.3. So when I plug into this formula, I end up with the probability that T is less than 3.3 minus 3.4 divided by 0.35 divided by the square root of 25. Well, 3.3 is the same, 3.4 is the same, 0.35 is the same, and 25 is the same. And when I solve this, I'm going to get exactly the same value as I have right here. So this is going to equal the probability that T is less than negative 1.4285. So once again, we have exactly the same values. But when we go to the calculator and we go to calculate the probability, we're going to find that our probability is a little bit different. Well, here we were working with a normal, and here we're working with a t-distribution, and we know it's a t-distribution because it's the sample value, the sample standard deviation. So instead of being a norm CDF, we're going to do a TCDF. All right. So we're going to go second vars, second quit, second vars, and then I'm going to go to number 6, which is a TCDF. And I ask for my lower bound. Well, that's nothing new, negative infinity. My T value is negative 1.4285. So that's the same. But now they don't ask me for my mean and standard deviation. Before they asked me for my mean and standard deviation, now they're asking me for my degrees of freedom. Well, what are my degrees of freedom? Well, my sample degrees of freedom follows this formula. So my degrees of freedom are going to be 25 minus 1, which is 24. So I can plug in 24 right here. And I can either type in 24 or I can type in 25 minus 1. It'll accept either one. And notice our probabilities are not the same. We have 0.0830 versus 0.0765. So this one is a little bit bigger. Why? The T distribution has more area in the tails than the normal. So very close, but this is a T distribution. And the reason we knew it was a T was because we were working with the standard deviation of the sample. Let's do one more of these to show the difference. So assuming that the duration of human pregnancies can be described as a normal model with a mean of 266, so we have a mean of 266. Suppose a certain obstetrician is currently providing prenatal care for 60 women, so we have an N of 60. What's the probability that the mean duration of these pregnancies will be less than 260 days if the standard deviation of the population, so here they give me the standard deviation of population is 16. So standard deviation is 16. And because I have the standard deviation of the population, this is going to be a Z. And they want the probability that's going to have an average of less than 260 days. So my X bar equals 260. And in this case, we're taking a sample of size 60. Now, if I'm drawing a picture of this, I don't have a whole lot of room, so that's why I'm putting it up here. This is my mean. My mean right here is going to be at 266 days. We have an X bar, so this is the mean. Our X bar is at 260, and we're looking for that area shaded off. This is supposed to be 260. All right, so this is going to negative infinity and positive infinity. Once again, we're working with a Z, and our Z formula is Z equals X bar minus mu sigma divided by the square root of N. So I'm looking for the probability that Z is less than 260 minus 266 over our standard deviation of 16 divided by the square root of 25. Now, once again, we're going to need to be pretty careful with the calculator as we get our Z value. So let's calculate our Z value. So I can go parenthesis 260 minus 266, close parenthesis, divided by parenthesis 16 divided by the square root of 25. That's my little, the 0.5 is the same as doing the square root, and I need to close my parenthesis off. And I end up getting negative 1.875. Well, if I were to go ahead and do a norm CDF for that, I would find that I had a lower of negative infinity, an upper of negative 1.875. And because we have a z-score, all z-scores have a mean of 0 and a standard deviation of 1. So let's do this on the calculator. Second vars, normal CDF, lower negative infinity, upper negative 1.875, mean of 0, standard deviation of 1. And we get 0.0303 is our answer. All right, and let's do this. So that's the long way. Let's go ahead and do this the shortcut. Stats test, z-test. And in this case, my mean was 266. My standard deviation of the population was 16. 260 was my X bar. I had a sample of size 60, less than. And by the way, I just copied those values from what I had written up here. And I did a calculate. And somehow or another, I got a different value. That's a little bit disturbing. So let me go back and make sure I have the right values here. Oh, I used the wrong sample size. This should have been a sample size 60. I apologize for that. So I'm going to go back and fix that. So this is going to change this value right here substantially. So let's go back and fix that so we can check this out, figure out if I have any other errors. So going back, we're going to go back to our original equation, parenthesis 260 minus 266, close parenthesis, divided by parenthesis 16 divided by 60 caret 0.5, close the parenthesis, and there we go. That's what we had before. So we end up with negative 2.9047. So now we're going to do a norm CDF of that. So second vars, normal CDF. And I'm just going to just change that to negative 2.9047. Mean is 0, standard deviation of 1. And we end up getting 0.0018. So a very, very small percentage of the women group likelihood that we'd get a group of 60 women who had an average pregnancy of less than 260 days. So stats test, z-test is much easier this way. And there we have negative 2.9047 and 0.0018. So we're going to do the same thing, but we're going to compare it to a t-test right here. So we're going to compare it to a t-test. So suppose an obstetrician is currently providing care to 60 women, so the same number of women, so the same sample size. What's the probability that the mean duration of these pregnancies will be less than 260? So we want the probability that X bar is less than 260, which is what we have up here. So we'll go ahead and write that, the probability that X bar less than 260. If the standard deviation of the sample is 16. So now we have the standard deviation of the sample. So this is going to make this a T because the standard deviation of the sample. So we have, here's what we have. We have mu equal to 266. X bar is 260. S is 16. N is 60. And our formula is T equals X bar minus mu S divided by the square root of N. And once again, drawing this picture here, we're still centered at 266. That's our mean. We have an X bar of 260. So everything so far is exactly the same, except our formula looks a little bit different. So the probability that T is less than, plugging in 260 minus 266 over 16 divided by the square root of 60. Well, these are exactly the same values, 260, 266, 16, and 16, square root of 60 and 60. So this is going to be the probability that T is less than that negative 2.9047. Let's just go ahead and check that real quickly. Parenthesis, since I messed it up earlier, 260 minus 266, close parenthesis, divided by 16 divided by 60 caret 0.5. And there we get the negative 2.9047. But because we use the standard deviation of the sample, we're now not using a normal CDF. We're required to use a TCDF, where my lower happens to be negative infinity. My upper is negative 2.9047. And let's go back in there real quickly. And we go second vars, TCDF, my lower negative infinity. So I can just load it up with a bunch of nines if I want to. My upper is negative 2.9047. And my degrees of freedom in this case is going to be that 60 minus 1. So I have 59 degrees of freedom. And I end up getting a value that's larger than this one. Why? There's more area in the tails. Now, to be honest with you, there's actually a shortcut to this. By the way, I'm going to write down the degrees of freedom is 60 minus 1. The shortcut to this is to go stat test t-test, and my mean is 266. My X bar was 260. My standard deviation is 16. So everything's in there. And sure enough, there's my negative 2.9047. And there's my 0.0025. That's the probability. So the main thing to get out of this is if you have the standard deviation of the sample, if this is what you have, the standard deviation of the sample, you have to use T. If you have the standard deviation of the population, you get to use Z. All right, so that will conclude that video.